Hello, everyone. Today I'll present my work with my colleague, Shnai Kafkas, actually equal contribution. We were supervised by Dr. Robert Wondar. We come from King Abdullah University of Science and Technology. And today we are talking more about text here and how to do named entity recognition, but with a little bit of a twist because we would like to use some unexplored ontology components to do that. So first, let's start with the motivation. First, maybe some of you are not familiar with named entity recognition. Basically, let's assume you have this piece of text. Actually, we took it from an article with the following PMID. And then let's assume what you want to identify are mentions of phenotypes in this piece of text. So in this case, what you would actually like to point out are the pieces of text highlighted in red. So bone loss, fractures, and stress. So these are phenotypes. But just giving this to the machine cannot discern whether each word is a phenotype or not. So you would like to teach it to do that. And when you do that, you're actually doing some. You can actually link literature and ontology, because once you know, you can actually find your entities of interest in text. Then you can access literature, you can analyze it, you can pre-process your data. You can actually even choose data for some later on curation that you will do. You can even expand your ontology if you actually find mentions of your classes that you're interested in. But let's talk a little bit about existing work, where traditionally people used dictionaries and rule-based methods to do this. And the reason why they used to do this is because these dictionaries are really fast and effective. However, they fail to recognize new concepts, because unless you actually have the exact name in your dictionary, you're not able to capture a mention of an entity unless you have the exact same name in your dictionary. And they also usually tend to fail to disambiguate context. So for instance, if you have words like cancer, which could be a star sign and it could also refer to some type of a disease, then there's no way for these methods, neither the dictionary nor the rule-based methods, to actually disambiguate unless you actually put really heavy rules. But that's really time consuming, and it's hard to do it. And then, of course, I think most of us are familiar with machine learning and how once it became really popular, it brought about many advances. And first it came with supervised models where it required curated instances. So experts would actually come, they would sit, they would read pieces of text, and they would say, okay, this is actually a mention of, say, like a phenotype or whatever is your entity of interest. And of course, this brings about some disadvantages because it's time consuming and can be costly, as you might imagine. Then some other methods came that are semi-supervised, so they require less curated instances, but they still do require curated instances. But a really nice variant of these machine learning models is the distantly supervised variant. It's basically a framework where you don't really need strictly correct instances to train your model, to train your machine to be able to do the job that you want, but you can give it a set of somewhat correct set of samples, and then you actually hope that it would learn the task that you wanted to learn. And actually, surprisingly, in the literature, you can see how it actually brought about competitive performance to even those of the supervised models. So I'm talking about methods like Bond, Patner, Kemner, Thinatager, and ConfMPU. You can even look all of these up. But really, some of them really achieved state-of-the-art results without the need of actually manually curated data sets. So the rationale behind this is they create these weakly labeled datasets. These are datasets that have noise, actually. So what they did was they took labels and synonyms from ontologies and vocabularies. So it could be something that looks a little bit like this. Let's say you're interested in diseases. So they went, for example, to disease ontology. You can get the names of the classes here. Then you go to text. and then you just annotate, let's say, for example, exact mentions, so it's like of these diseases. Then you present these to your model. You say, okay, well, here are some annotations. There could be some errors there, but I think with some confidence there will be correct patterns, correct samples, and then you train your model. Okay, and many of these actually, for example, Partner achieved really competitive state-of-the-art results. But these previous methods have mainly explored the use of labels and synonyms, but there are other components in the ontologies that remain unexplored. So in this work, it's really an explorative work, and where our aim is to mainly explore this rich knowledge that we have in ontologies, so not just labels and synonyms, but rather definitions and axioms as well. And we focus on diseases and phenotypes because of the high interest in these two concepts. So the overview here is, it might look a little bit too much, but trust me, it's very easy to follow. You have an ontology of interest depending on whatever entity you want. It's like a phenotype or a disease. We create our dictionary, and then we use it to label and to create this weekly labeled data set. And it depends. It depends on like which component we're trying to explore. So either labels and synonyms together, axioms or definitions, or even a combo. And then to be able to compare with other methods, which actually went to unannotated corpora and annotated them. We even went to PubMed, just to be able to compare with the ontology components. We create this distant data set, we train a model, BioBird, and then we test. Okay? This is just the overview, but let's talk a little bit about details. So for diseases, we use the disease ontology, and also we included the medic vocabulary because it's used in some of the data sets that we're using for testing. And for phenotypes, we used the human phenotype ontology. So if you remember previously, I talked about how we're going to create this dictionary to be able to create our weekly labeled dataset. So to create this dictionary, we extracted labels and synonyms from the respective ontology, so either the disease ontology or the human phenotype ontology. We filtered stop words, abbreviations, and gene names because some diseases might have. It's easy to confuse some diseases with gene names. And we even generated plural forms to be more inclusive. And just quick datasets. Quick statistics. For diseases, we have around 244,000 labels and synonyms, which correspond to, there's a typo here, 29,000 distinct concepts. And with phenotypes, around 79,000 labels and synonyms, which correspond to 14,000 almost distinct concepts. So in ontology, actually, let's say O has 4 main components. The classes and relations. I think this is pretty self-explanatory. Then you have this domain vocabulary. This refers to labels and synonyms that are linked to classes. With classes, you can think of them as like these identifiers and the relation between them. Then you have textual definitions. And we will actually see an example of like these textual definitions that exist in ontologies in a bit. And you also have formal axioms, which describe some relationships between these classes. So here are also some quick statistics on the number of labels and synonyms from DO and MEDIC and from HPO. Of course, we have more labels and synonyms from DO and MEDIC because we merged 2 resources. And the number of definitions that we have for both and the number of axioms. So here's an example of how we generate this distant data set. So let's say now we're looking at this class of interest with the following disease ontology ID. And if you actually look it up, the name of that class is livedoid vasculitis. And basically how we would represent it in the data set is that we would tell we would label it basically, the whole thing as a positive. So if you see it in bold, it means it's labeled as a positive. And then we go with the synonym. Of course, we just extract the vasculopathy. And then, of course, again, the whole thing is a positive. Then with axioms, we have, for instance, the this ID is a subclass of this ID. So we try to make this natural language friendly. So instead of saying subclass of, we say is a. And then because both correspond to classes in our ontology, then we grab the labels for these classes and substitute the ID mentions with the label mentions or the names of those classes. So instead of putting the IDs, we go livedoid vasculitis is a vasculitis. And with definitions, we just grab definitions and then we annotate with the dictionary whenever we find a mention, a disease mention. So in this case, vasculitis and then ulcers. And I hope this is clear. Next, as if you remember, I was saying these previous methods, they annotated some corpora, some unlabeled corpora. To be able to compare with them, what we did was we went to PubMed and we took the top hits and then we lexically annotated with the dictionary. Okay. Quick statistics is as follows: around 7,000 distinct concepts from HPO we were able to find. This corresponds to 74,000 distinct PubMed abstracts and titles. And for diseases, 8,400 concepts that correspond to 187,000 distinct PubMed abstracts and titles. Okay, so far I've discussed this part. Now we focus on the third part. Third part is very easy. Once you have your distant dataset where you label the positives and the negatives, you just can directly train a deep learning model. In this case, we use BioBird because, of course, the domain that it's domain specific to the domain that we're working with, which is ontology, phenotypes and diseases. And then we start testing. So to test, we used the following corpora. For diseases, we use the NCBI disease. It's a very popular corpus. It has splits, training and development and testing. And also for diseases to show how sensitive these methods are to changes in corpora, we use the mid-mentioned disease corpus. So, but we only use the test here. And for phenotypes, we took the phenotypes from mid-mentions and also the GSC plus test dataset, which is also a widely used dataset. So just to be clear, whenever we have our models, we are not using any curated instances. We're just using the weakly labeled ones. But to be able to compare with supervised models, we are using the training splits here, just on the supervised ones. So let's take a look at some results for diseases. So we have the two corpora here, NCBI disease and mid-mentioned disease. And we start with labels and synonyms, and we see how the performance, if you only use labels and synonyms, how the performance is lacking, because there's not enough context for the model to learn. Once you start including more things like axioms and definitions, then you start to see some improvement in the performance. So we're talking about F1 score here, so it's the harmonized measure of precision and recall. We start to see how it goes up. And then with literature abstracts, we see how it's like around 86. It's even higher than the definitions in Axiom. However, when we see the supervised model that is trained on the curated NCBI training set, we see how really, really high the score becomes, around 94%. So what we wanted to test was how much of this performance is actually dependent on the corpus. So we moved to another corpus and we're trying to see how things would play out differently in a different corpus. The things actually played out very nicely for us because you can look at the models trained on the curated and NCBI training set, how they're performing at around 66%. But our models that are trained on definitions and axioms are at 67%, and with the literature abstracts at around 68%. We see a somewhat similar story with phenotypes. Again, with labels and synonyms, it's not very good, but then once you move to definitions and axioms, there's a boost in performance. With literature abstracts, they do slightly better than definitions and axioms. And then with the models trained on the curated set, we see how they perform nicely. Again, when we change the dataset, the model trained on the curated mentioned training dataset performs poorly, and our model, which was trained on definitions and axioms, does better, although the literature abstracts do even better than us. And we'll discuss this in a bit. But overall, the supervised models, they seem to be sensitive to corporal changes, as we've seen both in diseases and phenotypes. So when you train them on the NCBI disease and then you use the same one to predict on the mid-mentions disease, you see how the performance drops. And similarly with phenotypes. And here we're looking at some nice ontology components that we've used, which are the definitions and axioms, and how they can actually help to develop named entity recognition models at the state-of-the-art level. So they're really close to these ones that are trained on literature abstracts, although you don't really have to go and annotate a big corpora to do this, so they save you both time and computation. And we see also how names and the synonyms in isolation perform poorly because they lack context, in particular negative context. Now we looked at phenotypes because we've seen how there's a huge discrepancy between our model trained on definitions and axioms and the ones trained on the literature abstracts, around 6% difference. And we selected 20 samples, randomly selected 20 false positive samples for error analysis. And we've actually discovered that these are positives uncovered by the curated annotations. We have an example here, for example, uniparental dystony in the following PMID. And you can actually go back later and check for yourself that it's actually a correct prediction from our side, but it was just not covered in the dataset, in the JC plus annotations. Now we also found some really nice things, which are zero-shot instances. These are classes or like concepts that are not covered by the model. So we've seen that these zero-shot instances were not covered by the models trained on literature abstracts, nor by the models on the curated datasets. But when we give an example here, this Angelman syndrome, we were able to annotate it. And it does not exist in HPO, in the corpus, but it was still captured by the model trained on definitions and axioms. And the reason behind that is because these models that are trained on literature abstracts, if the word Angelman syndrome was actually there, it wouldn't have been annotated, but it would have been annotated as a negative. So the model had already learned it as a negative, and then similarly for the curated dataset. So in conclusion, we've seen how the ontology components can provide a suitable corpus to build state-of-the-art competitive named entity recognition model. This gives us two advantages because you don't need to annotate a large number of abstracts, and you reduce both the computational and time overheads. And to the best of our knowledge, our work is the first work that uses ontology axioms to build disease and/or phenotype named entity recognition models. And these models that are trained on ontology components, they were capable of zero-shot learning because whenever you annotate really external corpora, and you don't find any mention in your dictionary, you explicitly tell the model that it's a negative and it learns it as a negative already. So that's another perk that you get. And in general, we provide a generic approach, and this can be explored with other ontologies for other concepts. And that's it. Thank you. If you have any questions, please let me know.